Hello everyone, my name is Josh Walter, and I've been working under Dr. Chongze Hu in the Department of Aerospace Engineering and Mechanics, and my project is Machine Learning of Grain Boundaries in High-Entropy Alloys. So first off, what are grain boundaries? So grain boundaries are defects where two or more crystalline structures meet inside a material. So in most materials, the crystalline structure is not uniform throughout the entirety of the material. They're at different angles, different shapes, and where they meet up, they obviously do not meet up evenly, and this causes disorder to occur. And this disorder can alter the material's properties, which is why we study it. So for our research in particular, we are studying high-entropy alloys. And high-entropy alloys are metal alloys, that contain 5 or more different elements. And currently, most research into metal alloys at grain boundaries tends to be focused in binary alloys, which are made up of primarily one element, maybe doped with a little more of another. But high-entropy alloys have unique properties because they are made up of 5 or more different elements in all large compositions. So that's why we are studying them. And we're also trying to demonstrate the usefulness in general of machine learning for materials research. We're trying to show that this can accurately be used to predict properties. We're also trying to understand grain boundaries, how these grain boundaries affect materials properties in general, and their uses in aerospace materials. So why are we using machine learning? So we're using machine learning because atomic simulations tend to be extremely computationally heavy. A lot of the simulations we're running, even using supercomputers, can take days to run. And when you're trying to verify all these different alloys, test all these different compositions, that takes a lot of time. However, if we can have a small set of data, and then from that data, we're able to use machine learning to predict different results, then it can save us a lot of time, as we will only have to test a few more simulations. And we can predict the properties through this. And one thing I should mention about my project is we are purely computational. So we're just trying to conduct these simulations and machine learning to create these ideas, and then other groups can then experimentally test these based off of these results, as it would take a ton of time to experimentally test all these different things. So for our project, we are using cobalt, nickel, chromium, iron, and manganese alloys. We are then using Bayesian optimization for our machine learning. And what we are trying to do is maximize and minimize absorption. And absorption is the tendency for elements to segregate to the grain boundaries. So in our case, we're trying to predict the segregation of chromium and manganese. And these elements have a tendency to segregate because in these metal alloys, there's a lot of different sizes of atoms. And these different sizes, shapes, create disorder in the bulk of the material. So if these elements that are causing the main bit of the disorder in the bulk segregate to the grain boundary, where there's already a lot of disorder, the overall energy of the system can be lowered. We are also trying to minimize and maximize the disorder in general, and then we are conducting molecular dynamics simulations to verify the results. So here's a quick graph of our project. We start with these molecular dynamics simulations, and we create a database of grain boundary properties. From that, we can use our Bayesian optimization and Thompson sampling to then create a suggested design based off the properties we are searching for. And then from that, we can test using simulation. So now, what is Bayesian optimization? Bayesian optimization is a way to use machine learning to predict results. So how it works is you have your original data set, and from that original data set, a probability curve will be generated. in our case, we are using a Gaussian process. And then we use an acquisition function, in our case, Thompson sampling, to pick exactly which points to test from that Gaussian process. And then after we test those points, then we'll take those into account as well. And we will keep narrowing down on what our function looks like by altering our hyperparameters, which control the behavior of our function, until we narrow down on a prediction of what the properties looks like. And then from that, we can generate the results that we desire. So here's a quick graph of our Bayesian optimization. In the gray is the points that we actually started with and ran molecular dynamics simulations on. Blue is then all the evaluated points from our Bayesian optimization. And the purple points were some of the top performing points from that Bayesian optimization that we then ran simulations on. So as I mentioned, we run our molecular dynamics simulations to then verify the results of our Bayesian optimization. And for these simulations, we use large-scale atomic molecularly massively parallel simulator, or LAMMPS code, to conduct them. And in that, we have a model of our grain boundary at the atomic scale, and then we can input what we want our distribution, our percentage composition of atoms to look like, and then there will be a randomized distribution of these atoms. And then we can run these simulations at different temperatures, and they basically simulate the mixing of a metal alloy and how these atoms will want to behave in that situation. And from that, we can then calculate segregation and disorder. So here's a graph of some of our molecular dynamics simulations results. On the left here is the minimum and maximum segregation that our Bayesian optimization model predicted, and then we conducted simulations on. And as you can see, there tended to be a lot more segregation of chromium and manganese in that second simulation, showing that our Bayesian optimization model tended to accurately predict these sort of results. And on the right is the minimum and maximum disorder that our Bayesian optimization model predicted. And center symmetry is a relative parameter that measures how ordered the atoms are relative to each other. And as you can see, there tended to be much more disorder in that second simulation as well. As for our future plans, we're going to work on continuing to modify our Bayesian optimization model. There were a few cases where we got somewhat unusual results, so we're going to go back and see if we need to modify any of our parameters to make sure everything's accurate. And from that, we're going to conduct more molecular dynamics simulations. And then additionally, we're going to be conducting more calculations on materials properties. Does anyone have any questions?
So what state are you modeling these alloys in? Are they in the solid state or liquid state? How are these atoms able to move around like that?
Sure. So we are simulating the mixing of these alloys. So they are in a liquid state, but yes.
What are the advantages of using the Bayesian optimization model that you talked about? Is there another machine learning model you could use?
So yes, there are absolutely more machine learning models that we could use, but we chose Bayesian optimization because it's computationally efficient. A lot of other machine learning models use things like random search, so you're trying all these different data points. Whereas Bayesian optimization, since it's taking past results into account and it keeps narrowing down upon that objective function, we're able to a lot more efficiently create the results that we desire.
Can you elaborate on sort of the broader implications of your research related to aerospace?
Sure. So probably the biggest benefit of our research is that machine learning model, Because if we can prove that it effectively is able to predict materials' properties, then it can be used in all sorts of other different situations, and you can predict things like strength, lightness of material, things like that, that overall will help the aerospace industry effectively speed up materials research and generate new alloys that are useful.
So how does that Thompson sampling work, and why are you using it?
So Thompson sampling is our acquisition function that is picking the points to test. And the big advantage of it is that it takes into account both your past results when it's picking points to test, but it also introduces an element of randomness so that you don't get stuck into a suboptimal solution, but you're still able to use those past results to then generate better future results.